together, sorry. So when you put it in the dielectric in a field, what happens is you get separation of charge. You actually form a dipole in the sphere. And so you have two sets of lines in the second picture. You have the uniform electric field, the horizontal lines, and then the induced fields that look like a dipole field. The sum of those two is what you really observe. And that's that. So the overall result is you get less field lines going through the material as you have on the outside. And so the bigger kappa is, the harder it is for the field lines to penetrate through the material. So if kappa is infinite, none of the field lines penetrate the material, because sigma equals sigma induced. Okay, so where are we at? I'm going to stop here, and I'm going to do some examples next time. And basically, I'm basically done with the chapter. The homework is due on the 16th. The 16th is Tuesday, right? I hope. Yeah, the 16th is Tuesday, so that's good. So I can do 2 more examples to help you do the homework, okay? So one of the examples, let me show you this example. This example I will talk about on Tuesday, but I did it completely in a video that I sent you a link to a video earlier today. Okay, and in that one, I went through gory details to solve that one. I solved for everything you could know. Okay, I went through every single detail you could know about that problem. That's a 22-minute video. Okay, so I went through all the details. I don't have the time to go through the details in lecture, so, and I haven't captioned it yet. I haven't had time to caption it yet, so I haven't put it on one of the modules, but I'm going to try to work on it over this weekend. Okay, so I have a couple more examples, and I want to, I don't know if you guys have a couple minutes, I can show you 2 more videos. Okay, there's just for fun. One of the applications of capacitors, it's an interesting one, is in musical instruments. Let me go to the musical instruments. I'm going to skip some of this stuff. So capacitors, we talked about them the other day. You see them in radios, keyboards, etc. But there's a musical instrument. Have you ever heard of that instrument? You know what it is called? It's basically a capacitor. Yes, it's a theremin. Good, great. So basically all you do is you're moving your hands in a capacitor, and that produces music. Okay. So if you go online, if you go on YouTube, you can actually find a video from 1929 where the original person who designed it is using the instrument. Yeah, the theremin. So there's interesting applications. One of the interesting applications of this. You saw it in Big Bang? Okay, I want to show you one, just for fun. I know I'm staying over, but just for fun, I want to show you another video. I'm done with the PowerPoint. Like I said, I'll do the examples next time. I want to show you just a fun video, I guess, of what happens, an example of a corona discharge. Okay, I want to show you an example of a corona discharge at a power plant. It's a very short video. Okay, here we go. So you get to see the size of the arc compared to the people there. Okay. That was just for fun. Okay, so anyway, I'll take a few minutes if you have questions on the homework. There's actually one I have to, one of the homework problems I have to correct a mistake in it. Okay, so, okay, Ratej, this, let me see, the sigma in the equation on the right is the same as the original. Yes, that's right. It's not connected to a source. Okay. So Jacob, you have a questions on the multimeter lab? Okay, go ahead and ask.
So it says to film yourself wiring the multimeter into the circuit. How would we go about doing that?
Say that again.
So for number 5, it says to film yourself wiring the multimeter into the circuit. How would we go about doing that?
Well, you're going to be measuring current, right?
Yeah.
So you put it in series. Right? You wired the light bulbs in series, right?
Yeah, light bulbs are in series.
In the first step, you hooked them up in series, correct?
Yes.
So then you hook up, you just replace one of the light bulbs with the meter. That's it. Other questions? No questions? Everyone's okay? Everyone's ready for the weekend? Okay, go ahead, Raftej. Well, try saying something, and then if it doesn't work out, then just go ahead and type it in, okay?
Let me type it. Can you hear me?
On and off, sorry. Jeez. You really got to complain to them.
Yeah, I'm so mad right now.
Yeah, Jacob, you can do it. I mean, there is no set way of, I mean, it's just in series. I mean, I used the light bulb as just as, I used the light bulb circuit just as an analogy. All you're doing is connecting two things in series. Okay, whether it doesn't matter what you put in series. I mean, when you hook up one object after the other, that's what it means in series. So, you know, as a picture, let me get a better marker, and I'll get your question, Ratesh. So if I have my light bulb like this and a second light bulb like this, the circuit's the same. I mean, same idea if I replace it with an ammeter. This is a map that tells you how to make the connections, right? Take the wire from the positive side of the battery, hook it up to one side of the bulb, The other side of the bulb goes to the positive side of the ammeter. The negative side of the ammeter goes back to ground, or just to the other side of the battery. Okay, that's it. Okay. I'll get to your question, Chase, next. Okay. Ravtej, can a conductor ever increase the capacitance of a capacitor? Let me think about that. Only in this sense. I'm trying to think. I'm trying not to make a general statement. I can't off the top of my head because the capacitor worksheet has you do this. This is the capacitor worksheet. This is the conductor. This is two capacitors basically in series. Yeah, I think it could. If you do something like this, right? Or you do something like this. Actually, this is probably more likely. This can't touch this. Is that okay, Ravtesh? Well, if I fill it completely, I'll make the capacitance 0. Okay, there was another question. I gotta scroll to the top here. Number 8 talks about breakdown voltage. So you saw that spark in the video, Chase? So the voltage that produces that arc is called a breakdown voltage. It's when a material will actually conduct electricity. Okay, so all materials eventually will conduct electricity if you put a high enough voltage. So I think for air, the maximum electric field basically is about 3 million volts per meter. So if you apply an electric field of over 3 million volts per meter in the atmosphere will ionize and conduct. And that becomes a problem. I used to work in the lab, and the person next to me in the lab they had an accelerator that ran over 100,000 volts, and it would break down a lot. So the accelerator had 2 covers, 2 conductors like this, separated by air. And when they ran over 100,000 volts, we'd be hearing tick, 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 because you get arcing in between 2 conductors. And so they actually had to go in and fill it up with a dielectric. You can't make a material you can't use a solid material really to do this because it's expensive. And so they ran a gas called sulfur hexafluoride in between the 2, in the space between the 2 conductors. And that fixed the problem. So all materials and all different gases have different breakdown voltages. Yeah, it's the voltage after breakdown. So we talk about the electric field voltage, but if you're talking about the voltage over a distance, then you talk about the breakdown voltage. Okay. So for example, in air, 3 million volts per meter, if you want to do it using inches, every 20 million, for every inch, if you have a potential difference of 20,000 volts, you'll ionize it. That would be the breakdown voltage over an inch. The breakdown voltage over a foot would be 12 times that. That's basically the voltage at which the material will conduct, given this thickness of the material. That's why it's better to actually talk about the field in which it breaks down. Is that okay, Chase? Okay. There's a lot of videos like the last one I showed you. They happen at power plants. Where was I? Did I answer everybody's questions so far? I think I did. Okay, any other questions? The multimeter work as I explained, that's good. And there's the video that I emailed you from Tyler. He goes through and he does a better job filming it. So you can take a look at Tyler's video too. Those of you, I emailed you the videos, but I also, those of you who are on Discord, I actually put the link on Discord. All you got to do is click the link on Discord and you'll see it. Other questions? No, I haven't graded a previous lab yet. You are correct, Jacob. I will get to it. So, usually at this time of the semester, I get behind in grading labs. It is really, for me, it's very time consuming to grade labs on Canvas. I almost think that I should download them, but then it would cost me a lot to print. If I download them and print them all, it's much faster to grade on paper than on the computer. I'm slow at typing, and the stylus for me doesn't work very well, so it takes me long. So I apologize for that, and I tend to try to grade the exam first because those are more important. Yeah, the videos, so the multimeter video, I probably might end up grading first because that's much faster to grade. And then I will grade the other one, the properties of charge one. Okay, the multimeter one, all I got to do is check that basically I'm checking boxes. Did you do this? Did you do this? So that was a lot easier to grade. So I can get that done quickly. It's the properties of charge takes forever. But by the break, I should have been caught up. I haven't looked at the lab. I'm sorry, Chase. I just haven't. Like yesterday, I was in meetings all day for various reasons, and they had really not much to do with teaching. But I was stuck in meetings. I will look at it. I will look at your comments. Okay. I do look at the comments or any questions students have regarding the lab. That's what I did last semester. So I got rid of the glass, even though I forgot to reboot it in the text of the document. Other questions? All right, take care, Chase. Anybody else have questions? If not, you guys have a good weekend. You folks have a good weekend, okay? All right, take care. All right. See you guys.